Cast is now starting. All attendees are in listen-only mode.
Welcome to the SOARCE webinar. We'll get started in just a moment. All right. If you wouldn't start recording.
Should be good to go.
Okay. Good morning, afternoon, and evening, everyone, depending on where you're coming to us from across the nation. Welcome, everyone. We're pleased to have you join us for the Sharing Ocean Acidification Resources for Communicators and Educators webinar series. The SOARCE webinar is presented by NOAA's National Marine Sanctuaries and NOAA's Ocean Acidification Program. Our goal is to provide ocean acidification communication tools for informal and formal educators and stakeholders across the nation to promote a more integrated and effective ocean acidification education community. Next slide. Today's presentation is Keeping It Real, Connecting Ocean Acidification to Watershed Health and Promoting Student Action. I'm Liz Parati, Education and Outreach Coordinator for NOAA's Ocean Acidification Program, and I'll be moderating today's session along with Julie Bursick, Education and Outreach Coordinator with the Channel Islands National Marine Sanctuary, and Liza Wright Fairbanks, the Canals Fellow with NOAA's Ocean Acidification Program. Thank you for all for being here today. We're glad to have over 100 registrants for today's webinar from across the states and globe, and all of you are scientists and educators or just interested in these topics. Next slide. During the presentation, all of our participants will be in listen-only mode. You're welcome to type questions related to technical issues or questions for our presenters into the questions box at the bottom of the control panel on the right hand of your screen. We'll be moderating incoming questions and we'll respond to them either in the chat or pose them to our speaker at the end of the presentation. We will also post links and resources that our speaker will be talking about today in the chat so you can follow along and add to your own resource collection. Also, we always welcome your input on who you would like to see as a future SOARCE webinar speaker and what topics and resources you'd like us to cover in upcoming webinars. If you have any ideas for us, please type those into the question box as well, and we'll take those into consideration as we move forward. We will be recording today's session, and the recording will be shared with all registered participants via the Google Drive and on NOAA's Ocean Acidification Program's YouTube channel. As we get started, I'd like to understand your current role. Liza, please launch the poll. First, please take a moment to tell us who you are. And if you are in the other category, please share your role with the audience in the question box. We'll just take a minute for everyone to add to the poll. And then, Liza, when you see there are some enough responses, why don't you show the results of the poll with the group?
Are you able to see those results?
No, I just see, maybe you could tell us what you're seeing on the results. Oh, here we go.
Yeah.
So we're seeing that we have a little bit over half of our visitors are from our educators. We also have about 18% science communicators, about a quarter scientists or researchers, and others who are populating in the questions box. And they include students, scientists, resource managers, and other people. Thanks for that, Liza. So next slide, please. So I'd like to welcome, and we're very pleased to have Dr. Jason Hodin speaking with us today. Jason is a senior research scientist at the University of Washington's Friday Harbor Labs. He earned his PhD in zoology at the University of Washington, studying insect metamorphosis, and then shifted directions to studying the amazing metamorphic life cycles of ocean animals, particularly sea urchins and sea stars. At Stanford's Hopkins Marine Station, he worked to produce digital content for students related to sea urchin embryology, and then partnered with a local high school teacher, Pam Miller, to produce the core content for the virtual urchin site and tool that he'll be talking about to you today. And this incorporates basic biology, microscopy, and ocean acidification. So please welcome Jason Hodin. And Jason, we're now going to turn it over to you. Please share your screen.
Okay, great. Thanks very much, and welcome to everybody. Thank you for coming, and thanks for the introduction there. Okay. All right, that is that's showing right now, the presentation. Let me put it into a different mode here. Put it into slideshow mode here. Okay. All right, so whoops. I think that it's going to do this once and then hopefully not do it again. Well, maybe I'm wrong. Okay, it wasn't doing this before. Sorry, it seemed to be in like automatic flow mode here. I'm gonna have to change this, sorry. Sorry about that. Not sure why I just decided to do this. Okay, let's see if I can get it to stop now. All right, I think we're good. Okay, sorry about that. Yeah, so I'm going to talk to you today about a topic that is of great interest to me as a human and a scientist and an educator, ocean acidification. I'll tell you a little bit later about how I came to find out about it, but what there's a pretty broad audience here. So there, maybe somebody in the audience who knows, or several of you who know a lot more about ocean acidification than I do, that would be fine. But I'll tell you what I know and what I've learned and how I've come to think about presenting it to students. The resources that I'm going to show you date back until the mid 2000s when we first started working on this. And recently we just did a major update. So for those of you in the audience who might be familiar with our ocean acidification virtual lab and activity online, maybe you haven't seen the fourth part of it on student action, which I really want to show you. Although I'll go back and, for the benefit of those who haven't seen it, and because we've done some updates, I'll show you the first parts as well. I want to start by acknowledging, first of all, that there's been a whole series of projects that have together produced and updated this content for virtual urchin, where this activity is housed, and related hands-on projects, which I'll talk about. And the core team members are shown on the top. The ocean acidification activity is translated into multiple languages, and those translators are shown here. And we work with a lot of partner organizations, especially in the context of workshops that we put on for teachers. And then I just want to show you this list of teachers who have literally directly worked with us on this content. We've run a series of workshops related to different aspects of these projects. And in each case, we've come away with a better understanding of how to tailor these activities so that they are useful to educators. And in one case, as I'll show you, they literally came up with a key analogy that we use in the fourth part on action. And then finally at the bottom, sponsors over the years of this project, which has been pieced together from a variety of funding. Okay, so I'm just going to ask this question, although you can go ahead and put your answer in the question box if you know it. Anybody recognize this statement? The oceans and humans are inextricably connected. Well, it's ocean literacy principle number 6. And this is often talked about in the context of humans are connected to the ocean, which is definitively true. However, it's often described as, maybe this sort of idea of what is the proportion of humans who live within 100 kilometers of the coastline. I actually like to ask the inverse question, because there's a lot of humans who don't live within 100 kilometers of the coastline. So, so this is the first poll. We have a poll on this that you can answer. You can give your best guess of what is the proportion of humans who do not live within 100 kilometers or 62 miles about of the coastline. So wait a minute for you to be able to put in your answers there. And it looks like we might have answers. Okay, so we've got a pretty evenly divided electorate here. No plurality, no majority. It's going to go to a runoff election. But let's kind of go back to the presentation here, and I'll tell you what the answer is. I don't know how to do that, by the way. Do I have control of that?
You should. You may need to select your screen again.
Okay. Oh, well, maybe I lost my presentation somehow. Ah, there we go. Okay. Is that showing? Doesn't seem to be. Ah, there we go. Okay. All right. The answer is 64%. And, honestly, even this question doesn't really address the issue of direct connection to the ocean. Like Liz mentioned in the beginning, I started working on this project when I was working down at Hopkins Marine Station. And I was teaching at the time in Salinas, which, if those of you are familiar with the geography in California, is much less than 100 kilometers from the coastline. It's more like, I don't know, 12? I'm gonna guess, or no, excuse me, that's about miles. Maybe it's 20 miles, 20 kilometers from the coastline, or maybe a little less. And there were a number of students in my community college class who had never been to the ocean, which may seem shocking to you, but it's different for a lot of different people for a lot of reasons. And so, so I think that we really do need to think about it for those of us who care about the ocean, which is all of us here. And understand how important the ocean is to climate and to the health of the planet and ourselves. We really need to rethink this issue of connection to the ocean. And the obvious, and as we all know, we are not only connected to the ocean through the ocean itself, we're connected to the ocean through water and watersheds. And so that's a big part of one of the ideas that I want to talk to you about, and I'm going to hold that aside for a little bit. Let's move on to a second question here. The ocean is a major influence on weather and climate. Okay, I'm not going to poll you on this, but you might recognize that as ocean literacy principle number 3. And so in this context, here's another poll question for you. The ocean absorbs what % of the carbon dioxide that we add to the atmosphere? So can you show that poll, please? All right, so you see your choices there. You can go ahead and put your answers in. All right, and looks like we're about to get the responses. All right, so the responses are the majority, or the plurality, excuse me, believe that it's 50%, and then it's sort of evenly divided between 30 and 75%. So let's have a look at the answer. The answer is about 30%. So, and here is the context that I want to bring up that number with you. So, in the time before ocean acidification was on our radar, and by our, I mean almost everybody, including most scientists and most ocean scientists, to be perfectly honest, our response to this was, great, the ocean is absorbing 30% of the CO2 that we add to the atmosphere. That means that that's 30% less CO2 that could be contributing to global warming. We thought the oceans were doing us a great service, and of course, in some ways they were. But then when finally we recognized that actually all of this carbon entering the ocean is changing the chemistry of the ocean, we're like, the ocean absorbs 30% of the carbon dioxide that we add to the atmosphere? OMG. You know, and here's the context that I want to just, tell you really, really briefly how I came to find out about all of this. I was at Hopkins Marine Station. This was in about 2006. We were just getting ready to launch the website Virtual Urchin with our core content, which started with a sea urchin fertilization lab and some microscopy resources that we were working on. And I was at a seminar that was being given to the Hopkins Marine Station scientific community. The audience was full of mostly scientists, marine biologists, and others from Hopkins Marine Station, as well as members of the community. We're right next door to the Seattle Aquarium. Some of those folks sometimes attend, and a lot of scientists in the region like to come. So a packed house, and it was about this topic that basically none of us in the audience had heard about, which was ocean acidification. It was about 2008 at the time, I guess, about 2007 at the time. The presenter, Peter Brewer, was telling us about ocean acidification and the impacts that it could have. And at that time, the predominant idea, the impact that it could have on calcification, on the formation of shells of marine organisms that we know and love. And I'm sitting in the audience. I happen to be sitting towards the front, and I turned around to kind of look back. And I mean, I've never looked at an audience before in which it literally seemed as though everybody's jaw was on the ground. I mean, their mouths were agape all over the audience. This was a bunch of the most, well-trained and well-read and well-published scientists on the planet at Stanford University, and nobody had heard about this. So, because we were putting together this site on Virtual Urchin, because we wanted to do something on an environmental issue, and because we were talking about a shelled organism, and urchins are a shelled organism, we decided that we would look into this and think about putting together some content related to ocean acidification. We ended up partnering with scientist Sam DuPont and his team out at the Sven Löfven Center in Sweden, and some educators out there, and produced a virtual lab, which I will show you. And that was launched at around 2008, I believe, and it had been up there for more than 10 years without being updated until we just recently got some funding from NOAA Ocean Acidification Program to update it. And so I'm going to show you the original activity. I'm going to show you our updates to it, and then I'm going to show you the additional part on student action. Excuse me. So let me, sorry, let me just, I'm sorry, I'm having a little bit of a problem manipulating this on my small screen here. Bear with me for just a moment.
The audience can follow along with Jason using the link in the chat to the Virtual Urchin tool.
Yeah, that would be great. Thank you. Every time I'm just about to, all right. Just gonna quit this. Okay, finally figured out a way to get out of there. Okay, so what I'm going to show you now is, sorry about that. You can all see the Virtual Urchin website now. You can go to this and follow along, as Liz said. You can go to virtualurchin.org. It will take you to this main website. And so you can see what the different tutorials we have. And here is Our Acidifying Ocean right here, which I will launch. And this is the opening page of part 1. It's a 4-part activity. It's got background in part 1, a virtual lab bench in part 2 where you set up the ocean acidification experiment, a lab analysis, part 3 where you do measurements, and part 4 is the part on student action. And I just want to point out to you, although I'm not going to show you, that over here on the left side, you can select language. Feel free to do that. And it turns out that Our Acidifying Ocean is actually the only one that we've received funding and have been able to produce in multiple languages. And if you want to follow in another language, we have German, French, Spanish, English, and Portuguese. Feel free to select that language and follow along. So I'm going to just show you some highlights from this opening part. And I'm going to go to this page, for example. So up here on the top, I'm clicking this sort of what's called in the business a breadcrumb, which shows the different pages. What you normally do is you push the arrows to page through, and you can select your part at the top. And this is another learn, experiment, analyze, and act is another name for the 4 parts. So that's how you navigate around. This is the famous Keeling curve, and this page talks about carbon dioxide in the atmosphere, where it comes from, and it goes into detail to describe why does this have a wavy blue line here and also a purple line in the background. Why is there a solid line and a wavy blue line on this graph? That's explained down there on the bottom. And I also want to point out one of the places on the site where we have added something recently. If you haven't been back to the site in a while and you haven't seen our latest updates, these buttons down at the bottom, in this case, it's a button called Dig Deeper. If you click on that, it will take you to the Scripps Institute website to learn more about the Keeling curve and where it came from and long-term data sets. And then there's more on NASA's Climate Science Investigation site. So make sure not to miss those boxes at the bottom. They sometimes provide additional help, and they sometimes provide additional content. So it can help you. One of the advantages of doing these things on the web is we like to be able to provide content to assist students who need a little more assistance, and to provide more information to those who may be, more advanced on this topic and already know something about it and want a little bit more of a challenge. Then we have a little activity here on pH, which maybe is similar to things that you might do with your students. And this is a little drag and drop game. We have some common household liquids here and other liquids, and where they would go on a pH chart. So let me just ask you to, and I don't know if we actually have a poll about this or if this is just a question that you can just put your answers in the chat. Here are some little liquids. Let's go with Coca-Cola. Anybody know what the pH of Coca-Cola is? So it looks like we don't have a poll on this, but you can just go ahead and answer your questions in the question box, and if you know, and we'll see what y'all might have to say.
I'm seeing some responses of 3, pH of 3.
Okay. Yeah, I mean, I was afraid of this when I saw that high percentage of scientists and probably some ringer educators in the audience that you all are way ahead of me. That's right. It is about 2.5 to 3 is the pH of Coca-Cola. So as you can tell, this talk is brought to you by the Coca-Cola Bottling Company. Okay, moving on. Here's the graph of ocean pH, and you can roll over these values here to see how it's changed recently. And so we can look at the present. So compressed all the way to the right side of this timeline, which is millions of years, you can see that how quickly the mean ocean pH has been dropping, and if we continue on the path we're going on, where it's going to drop to, which is way outside the normal range. Now, these amounts are not outside the kinds of ranges of pH that we do observe sometimes in the ocean, which we don't go into here, although some of that information is shown at the bottom in some of those dig deeper comments. And you can see here a couple of other buttons have appeared on this page for hands-on activities related to ocean pH, and the great unknown, which is the button about things that the scientific community still has to learn. And you can explore that in your own time. Plus, by the way, there's some little rollovers for additional assistance, like with the concept of logarithmic. And so you can roll over those things for help. And so as what I was going to say though is that the mean pH has stayed relatively stable, while ocean pH can vary tremendously. For example, in the intertidal on a diurnal basis, there can be huge fluctuations in the pH, and depending on whether you're in the near shore and at what point during an upwelling in the season. So we know there's a lot of variation in this, but these are mean values, and it's quite shocking. And so you can, when you think about these amounts, and you think about the issue of, well, 7.6 is pH that some parts of the ocean sometimes experience, what you should think about is that that's the mean then that's predicted, and the variation will be a variation around that. So the presumption is that in areas that experience low pH right now are going to experience even lower pH when the mean pH drops, and I think that's fair to conclude. So I'm not going to go through the chemistry, but here you can roll over the different parts of the chemistry and CO2 going into the ocean, turning into carbonic acid, and being converted through a series of equilibrium reactions to bicarbonate and carbonate. And please feel free to go here. I'm not going to take the time to sort of talk about the topic of ocean acidification specifically, but we have some background here for you about all the chemistry for you and your students. The key here, though, for the point of view of calcification, is that carbonate is levels decrease as a result of an increase in carbon dioxide in the ocean, because the equilibrium reactions are driven away from carbonate by the extra hydrogen. And so you end up with less carbonate to form calcium carbonate, and hence problems for calcium carbonate skeleton forming organisms like sea urchins and coral in this case, and many, many others. These aren't the only effects of ocean acidification, but were some of the first ones, and relevant to sea urchins, it's one of the major ones. Okay, so to continue on, but what I do want to show you here is that this still, I believe, is the only real interactive model of ocean acidification on the web. And we've updated it now with the most updated data. It's now dated so that the current year is shown as 2020, and you can do a couple of things here. You can set your scenario, which is the future emission scenario. Optimistic is like, we all wake up tomorrow and decide we need to do something about this and stop emitting right now. And pessimistic is, we're going to go on with the carbon burning party indefinitely. And then there's like a mid-range scenario. And these are based on the IPCC scenarios. And you can read more about it on this page. But what you can do is set your scenario. So let's set a middle ground scenario. And then what you can do is you can drag this slider forward in time. And what you can see is the values on the right changing as CO2 increases. And you can see the icons on the left changing in proportion, showing you how that will change the amount of bicarbonate, carbonate, and the amount for calcium carbonate. And what you can see inside this circle is a little kind of blow up, let's say a microscopic view of a coral skeleton, showing you that its calcification is being impacted, that it cannot calcify as easily under those future ocean acidification scenarios. And then you can change between the different scenarios at a given year, and you can see the differences. So I'll let you play around with that too. And the instructions are at the bottom, and more buttons and so forth. That's about all I want to show you about part one. There's a drag and drop game about calcifiers and non-calcifiers, which some of you might use as a hands-on activity in your class. There's information about the life cycle of sea urchins, since that's what we're talking about. And then there's sort of a summary again. And then we go to part two. Part two is the ocean acidification lab bench. The lab bench is used a few different times on the virtual urchin site to set up experiments, and in this case, we're setting up an ocean acidification experiment. The experiment is raising sea urchin larvae under two different ocean acidification conditions. And I'm not going to go through the whole lab with you. I've skipped forward in time in the lab just to show you a couple of the features here. What's happened at this point is that the student has set up the experiment with replicates. You can see these little jars. We've got larvae in these jars. There's 3 replicates at 2 different pHs, pH 8.1, current mean pH, pH 7.7, future ocean acidification conditions, and we are growing our larvae with algae food here, and about to do a water change and take a look at what is happening with our larvae after 2 days in culture. So we're going to start step 2 real quick, stop, and then we'll follow the directions. We take a drop of algae, we add it to a flask of already prepared seawater at the 2 different pHs. We take our jars off of the shakers, and then we're going to measure the pH. And at this stage, these jars had lids closed, and they started at a pH of 7.7 and 8.1, and we're going to find out what's the pH now after 2 days. And we're going to look down here, and we can see that the pH has gone from 7.70 to 7.73. And then the pH in the 8.1 is still 8.1. And the note tells us that if this were a real experiment, we would measure the pH in all 6 jars. We've done a lot of shortcutting in this experiment so that your students don't have to take 4 full days to do the experiment. They can do it in 20 minutes or so. And then it asks them the question, why did the pH increase in the 7.7 jars but not in the 8.1 jars? And I must have forgotten to tighten the lids. 8.1 is the highest possible pH for seawater. The pH in the jars is influenced by atmospheric CO2 level, which currently results in a pH of 8.1 after equilibration and all the above. And the answer is C. We check our answer, we got it correct, and then we can move on. And the next thing we would do is, well, we're going to answer some more questions. We're going to take a look at the larvae in the microscope, and we're going to continue to raise them for 2 more days, and then finally set up the experiment for analysis. And we're going to go on and do that part, which is part 3. So we could skip forward to part 3 at this point. And I'm just going to show you really quickly. These are the instructions, and I'm not going to go through the instructions. I'm going to actually skip forward like as if we were in a cooking show and show you that I've measured the larvae. What happens is you take the slides, you click on them, and every student gets a single larva at random from each of the replicates. And there's actually 5 larvae in each replicate, but they only get 1 of them. And they're asked to measure them by taking this ruler, putting it alongside, and reading off a number and sticking it in the space. I've already done that for you. So let's page forward, and it's telling me I haven't done it, but I actually have, because I paged forward and back again just to show you. And here's our full data. So my larvae are the 3 that I measured from each of the 2 pHs. The complete data set is on the right. If you do this with your students, you could actually do the complete data set yourself. You could gather all the data from all the students and make your own class data set. But we've done that for you with the actual 15 different pictures. And you can look at it in graphical form. And what you see is maybe there's a tiny bit of difference when I looked at my own larvae, but the complete data set shows a bigger cell separation. We're showing statistics here, standard deviations. Again, I'm not going to go in detail, but there's a lot you can do with your students about learning statistics, graphing data, and so forth. So it hits a lot of the kinds of things you might want to do with your students in general in science class. So I'm gonna leave the presentation now and go back to just show you a couple of things real quick here. Let's stop the screen share. Let's see if I can bring this back up.
We also have about 10 minutes.
Thank you. All right. All right, I'm just going to quickly show you this. Okay. So one of the things that we were concerned about is back in the mode where it's going forward on me, is that we want to have students be connected to this issue of ocean acidification. Again, a lot of students have never even been to the ocean, much less necessarily care that much about it or about a sea urchin. So we want to broaden the issue for them, and that's what the last part of this is about. We know we can act to reduce CO2 emissions, and that's and we have a project called the International Student Carbon Footprint Challenge, which the websites are in the chat, I believe. You can go to it and check it out. Your students can calculate their carbon footprints and participate in conversations with other students around the world about their footprints. We think this is an important thing, but we also realize that there is a bit of a problem in that the more that we know about climate change, and this is a societal problem, that the problem just appears really, really huge and hard for us to get to. And so in a nutshell, since I'm running a little bit over, I'm just going to skip and tell you that the solution that we've come up with for the psychological climate paradox, which is suggested by the literature, is to make it more real and something that students can do something about on a local level. And students can, and this is why. And it's shown in the back in the part 4 of the ocean acidification activity. And so this is the part on action. And the idea is connected to the notion of multi-stressors. So let me first just start by saying what we mean by multi-stressors, and this is the analogy that those teachers that I mentioned came up with. It's kind of like a student that has the common cold, all right? We know that the common cold virus can cause a cold. But we also know that other aspects of their life, including other stresses like social stress or poor sleep or an unhealthy diet, can contribute to that sickness. And when that student instead reduces those other stressors, that can lessen the effect of the common cold virus on producing the cold. And in a similar way, the ocean is also facing multiple stressors. It's not just carbon dioxide causing global warming and warming of the oceans and ocean acidification. There's all these other stressors as well. And the main take-home story that I want to tell you is that the way that we believe in what we're proposing in this action to localize this and make this real and in a totally legitimate way, and what we believe is an effective way for students, is that these other stressors, unlike carbon dioxide, which is a long-term global problem, that their individual actions will only be a drop in the bucket, truly, we still think that people should reduce their emissions and model that behavior. But these other actions are really important actions that we can do right now, starting today, and have immediate positive effects on the ocean. So if we can click on that, we can see the comparison between that stressed out nearshore ecosystem and this healthy nearshore ecosystem, which dams have been removed, sustainable farming to prevent fertilizer runoff and reforestation, clean energy instead of fossil fuels with spills in the ocean, and marine protected areas. Okay, so these are the kind of things politically, socially, individually, in a local community level that can be done in order to care for our watersheds and hence our nearshore oceans. So this closes the circle, if you will, to be able to connect these things to student action. And then I'll just finally show you really quickly that to bring this really home for students, we have a series of videos. I heard that those of you who were at the last SOARCE webinar saw this video already. We have some clips from it talking about Olympic coast communities directly addressing ocean acidification and climate change. And then here, for students in particular, this Me to We page talks about how individual action is part of a stepping stone. So just a really quick little, let's say, editorial comment on my part. There's a number of commenters lately who have been saying things like carbon footprint calculators and talking about individual action is taking our eye off the ball of the main responsibility for climate change, which is large corporations and big multinational entities and governments. And I don't think that's wrong, but I can't be more strong in my rejection of the idea that the individual action is not important. And if only for this, in that it is absolutely demonstrably true that individual action is a gateway to school level, community level, and larger scale political action. That is demonstrably true. And that in and of itself tells you that the focus on individual action is important if done in the broader context. And here we present that in the way of talking about me to we. So me starting at personal level, going to the school and community, and you can click on these and it shows some really inspiring stories from the Alliance for Climate Education and mostly, as well as another story from the Pacific Northwest in youth that are doing something about climate to inspire your students. And then after they've watched that, then they have the opportunity to fill out this form, which is their pledges on a personal level, on a school level, and on a community level that they will take, that they're pledging to take in order to take action. And at the end, they get a certificate with the information that they printed on there to be able to print out, hang up on the wall for inspiration, and use as they move forward through their education and through their lives. So that is it. That's what we're doing. I just want to really quickly end by showing you that this website, Inquiry to Student Environmental Action, which you see the link on, has got basically, it's our umbrella website to all of our environmental projects. So you can actually get to Our Acidifying Ocean this way. It'll take you to the virtual ocean site. Or you can go to the carbon footprint calculator. And then I want to just show you really quickly 2 different activities, Bonds Across the Water, and this one, Follow the Water, in which we worked with teachers to look explicitly at this connection between watersheds and the ocean, looking at the issue of multi-stressors. And so there's more information about multi-stressors here on the Follow the Water page and on the Bonds Across the Water page, with some links to some scientific papers on the subject, because this issue of multi-stressors is actually in the forefront of science. It's not just something, for you to present to your students as a motivational factor. It's actually what scientists think about when they think about climate change. And those pictures showing are from our workshop in California. All right, so that's about it. And I think that I went maybe just a couple minutes over here, but there should be plenty of time for your questions, and I'm happy to take them and go into any more detail on any of those things that I just really, really quickly rushed through for you. So, thanks for listening. And the one final thing that I want to say, so I don't forget, is that I'm very easy to find on the web. My other research side of my work is on sea urchins and sea stars. Right now I'm involved in a big project related to growing sunflower stars, an endangered species in the lab here at Friday Harbor Labs. And I'm not too proud to boast about the fact that if you go to Google and just search for sea star Jason, I'm #1 on Google. So you can find me that way and email me anytime you want to with anything, including observations of sunflower stars in the wild, by the way, which I love getting. So that's it, and happy to take your questions.
Great, thank you, Jason, for a really informative and engaging presentation. This was a great educational tool, and in case you missed it, we did put the link to the virtual urchin tool in the chat, along with some of the links to the other resources that Jason talked about as well. I'm going to turn it over to Liza, who's going to moderate our question and answer session. So feel free to post your questions in the question box.
Great. Thank you, Liz, and thank you, Jason, for your presentation. So please, if you have questions, pop them into the question box and we'll ask as they roll in. We have a couple to start with already. So first question is, have you seen a difference in who is using the tool since the first major update? And kind of following on to that, what kind of feedback have you received from teachers who have used the tool?
Yeah, those are great questions. Let me answer it slightly, maybe different way than it was intended, and just tell you that when we first designed Virtual Urchin, I think you heard that I was working with a really talented high school teacher, Pam Miller. This started as an expansion on a website that's called Sea Urchin Embryology, which still exists. And actually, it's about to get shut down on Stanford for those of you who listen to it. So I'm desperately trying to move it to the University of Washington server so we can keep that up there for teachers. It's basically support for doing sea urchin fertilization in the class as a great way to teach about things like mitosis and meiosis and topics that may not be so exciting to your students when seen in a static slide. That led to that website is for teachers, and the Virtual Urchin website was a grant that David Epple, who's the PI on that project and is now retired and has passed the projects on to me, and Pam Miller and others wrote before I met them to get that, to do something a little bit more focused on students. And really it was an idea of putting together support for students related to that sea urchin fertilization activity. And so we designed, the first thing that we did on Virtual Urchin was design a virtual version of a sea urchin fertilization lab. And then we realized that teachers wanted help with microscopy, and we started adding things because Pam knew, and we also had a lot of colleagues telling us what were the kind of tools that would be the most useful. And so we're adding things like that. And then we added this one on ocean acidification. All along, we were focusing our efforts mostly at the high school level. But we found out that the ocean acidification activity was being very broadly used at the college level as well. And so we really, really try to make it, you know, advanced enough for college students, but not too advanced so that it will be over the head of high school students. We've really tried to strike a balance in that way. And those little buttons in the bottom in some ways are an attempt also to try to bridge those gaps. But, you know, we think we maybe have tried to hit about that level of high school, you know, or early college sort of a level. And those are most of the people that we see using the site and still using it. We actually have not gotten a huge amount of like additional feedback outside the ones that the teachers we specifically worked with in designing this. So we did get quite a bit of feedback about that background part, and we got some ideas of things that we'd like to do, some that we were able to change and that are already changed in the version that you see now, and other ones that we have as a nice little wish list. I've got a whole folder on my computer of wish lists for Virtual Urchin and wish lists for I2C that when we get the big money from, you know, grants that we want to get, you know, we're going to put it into effect. Right now, you know, most of our time is, you know, volunteer on the project. And then when we get grants, like we got from the Ocean Acidification Program, we're ready to go. We got ideas and we put them into effect and we program them and we put them out there for you. But we're always looking for feedback, some of which I can go in and just be like, that's a great idea. I can add that right now. And other things I'm like, okay, that's a really excellent idea, but we need $10,000 for that. And then we look for the funds. So I hope that answers your question somewhat.
This might be a good time to launch our last poll on how likely our audience is to use this tool.
Thanks.
And that poll is now open. So while people are answering that, you talked a little bit about the different age groups that use this tool, and we have a question about what tips do you have for tailoring educational materials to different age groups?
Yeah, I mean, you know, you know, almost everything that I know about teaching, I learned from somebody else. I mean, I do some college teaching and, you know, but like, you know, working with these high school teachers, it's really a whole different ballgame. You know, I get exhausted after an hour and a half of teaching and they're teaching all day, every day. So, you know, I'm going to tell you just what I've picked up, which is, you know, we've always thought the Virtual Urchin website is a companion to hands-on activities. You know, there is nothing better than doing a sea urchin fertilization and looking in the microscope and seeing the fertilization membrane come up. You can't totally duplicate that online, but we also know that most classrooms do not have the capacity to get sea urchins and do this experiment themselves. So therefore, you know, doing the virtual is the next best step. And then we've got ideas. There's ideas on that Sea Urchin Embryology website for things you can do with your students in lieu of that. Along those lines, if you go to the, I think the link might be there in the chat, but if you go to the Bonds Across the Water or the Follow the Water site, there's links to a Google Drive where we've put together a whole bunch of hands-on activities. And some of them are linked, by the way, and there's little buttons on the bottom for hands-on. And what I would say is the best way to present these things to students is to do both, is to use our simulation and to pick a few of these kinds of activities, whether there's some really cool Lego activities for building the chemical structures of ocean acidification. There are some great little you can extract red cabbage juice as a pH indicator and do things like blow bubbles into it and show how the CO2 actually changes the color. I mean, so there's some really, really cool hands-on things that bring home some of these concepts of, like, for example, CO2 will go into equilibrium with the ocean. You can model that, and what effect that has in terms of changing the pH. You can model that. And so, having them see about it, work with our virtual tool is great, and then doing a little bit of hands-on stuff even better, and putting the two together is the best thing of all. And I will just say that, as far as the Virtual Urchin website and the I2C website, Virtual Urchin went over 1 million hits in 2021 for the first time. And the reason for that, I mean, it was, many hundreds of thousands before that, but the reason for that was the pandemic. Teachers were desperately seeking online tools to replace all the things that they do with their students. And so while we don't consider it a replacement, at least it's something. And, and that, I think, speaks to the fact that, it at least gives you some of that content. But the best thing of all, as you all know, is doing things with your hands literally. So, so that's what I'd recommend.
Great, thank you. And the link to further resources is in the chat for anyone who's interested there.
And if you have any questions about that, let me know.
Yeah. So we have one comment. Fantastic talk. I love how the larval measurements and comparing treatments with the tool demystifies what doing some aspects of science look like to students. And then
can I make a comment on that, please? I'm sorry. Can I make a comment on that comment?
Yeah, go ahead.
Really quickly, I don't think I mentioned this, but one of the really cool things that you'll find, I sort of like reloaded the page a bunch of times to try to get this certain data set. There is a chance that that there actually won't be a difference at all because of the variation in the larvae. If you only have 3 larvae, there's no difference. And so certain students might get that. And I was actually trying to get that magic set of larvae, and I didn't get it when I was trying, so I just got a close one. But if you do it with your students, somebody's going to get one in which the 3 larvae that they measure for pH 7.7 and 8.1 are no different from one another at all. I mean, and so that's a really, really important lesson about not only replication, but replication within replicates. In this case, the larvae are individuals within a replicate. And so you need to do a bunch of measurements, and you need to do multiple replicates in order to be able to come to some sort of reasonable conclusion. And sometimes you might get lucky by doing very few measurements and seeing like you see a difference, but you do enough of them and you'll see that there's a certain number that you really need to do. And you can go ahead and use this raw data. There's a link to download a Excel spreadsheet with all the raw data too in there, and so you can play around with it as much as you want.
Awesome. All right. We have another question kind of about the science. So you mentioned you're an urchin biologist. Can you talk a little bit about the urchin research behind the tool and why it was featured in this tool?
Yeah. Well, I mean, the reason it's featured in this tool is because I'm completely biased, and I love sea urchin larvae. But no, I mean, honestly though, I truly, I'll just tell you a little bit since you asked me. It's giving me a license to tell you why I think urchins are so amazing, which is my favorite thing about them is their metamorphosis. And when you were looking at those images of urchin larvae, many of you may not have ever seen an urchin larva before. We didn't even pause to, sort of reflect on the incredible nature of what a sea urchin larva looks like. But what you may have noticed is it doesn't really look like an adult urchin. It does have a skeleton, but it doesn't have it displayed in the same way. It's not the same structure as an urchin spine, and although it's made of calcium carbonate in both cases. And so they undergo this unbelievable metamorphosis between a bilaterally symmetric larval form and a radially symmetric adult with 5 sides. And because of that, that's why I wanted to study them in the first place. And quarter century later, have thousands of more ideas of things to study than I started with, and I'll never run out of things interesting to do with them. And so, but I actually do think that the sea urchin larva, with its skeleton and its larval arm that is a measurable entity, makes a very good choice of something to be able to look at quantitative effects of something like ocean acidification, because you can see the growth and you can measure it in a very, very clear way. Which your students will be able to do and see. It's not like a difficult, it's not so much of a judgment call, it's pretty clear what you're measuring. And so, and it's a structure that's made of calcium carbonate, which we know is related to the chemistry. So for all those reasons, I think it's actually a quite good choice in addition to being right up my alley.
Awesome. Great. I just want to remind the audience that if you have any more questions, please pop them into the questions box on the control panel. We have one here. It is great that this is available in several languages. Can you talk about platform accessibility? Is it also available for use on mobile devices?
Wow, it's almost like I planted that since I completely forgot to say it. Yeah, so yes, those of you who've been using Virtual Urchin for a while might remember that the entire site was programmed in Flash, which seemed like which actually was a great choice in 2005. There wasn't any other multimedia to be able to do the kinds of things that we wanted to do that was out there. But it became a terrible choice in the 2010s, especially towards the end of the decade, when especially Apple devices didn't support Flash at all, and then Adobe basically decided we're not going to keep going with the web plugins. So we managed to get some funding. Part of the funding actually came from this Ocean Acidification Program. We got some from a few other sources along the way, and managed to reprogram the entire Virtual Urchin site in Flash. And actually, our carbon footprint calculator was in Flash too. We had to redo that. So everything that we have is now no longer in Flash, which is wonderful. And one side benefit of that is that it can be used on any kind of device. We think, though, that at least the interactive elements kind of need like at least a tablet-sized screen, if not a really big cell phone. I mean, my cell phone, which is a tiny one, when I try to do it, it's doable, but it's, and I'm not very good with them. The students are probably way better, or are definitely way better. But moving those things around the lab bench, for example, excuse me, is a little challenging at that small screen size. But if that's all you got, it should be totally workable. And if you're having any issues with any kind of device or anything, please let us know about it, and we'll try to fix it. But it should work on all devices.
Awesome, thank you. We're getting to the end of our time here, so I'll just read a couple last comments that came in. One, I remember Flash, that is old, and a couple comments about a terrific website, and thank you, and this is a great tool. So I think with that, I will hand it back over to Liz to close us out. Thank you, Jason.
Liz, can I interrupt you for just a second and just remind people that if you had burning questions that I'm not looking at the question, if there was any in there that didn't get answered, or if you have any other ones, just email me, please.
Great, and we did put a link to your website with your email address in the chat as well, in case people can't find Sea Urchin Jason or Sea Star Jason on Google. So I wanted to thank you again for this great presentation. We will be sharing the recording and the links to resources mentioned today. Will be added to that Google Drive for the SOARCE webinars, and the video will be on our YouTube channel. Again, as Jason mentioned, if you have any further questions that pop up in your head later, please feel free to contact him directly. We welcome any feedback on this webinar or future suggestions for future webinars, you can submit your input by replying to the follow-up email that you're going to receive as a registrant, or by contacting us in the emails listed on this slide. So that's me and Julie as your primary contacts. And we would greatly appreciate if you would take a few moments to complete that feedback survey that you're going to get, because it allows us to continue hosting this webinar series. So with that, this is the end of today's session, and we thank everyone for your time and attending this great presentation. And thank you again, Jason.
Thanks, bye.